Awesome. So I'm thinking we should probably get started. We're hitting 10:20 here. So hi, I'm Leo, the founder of Graphistry, so a visual graph AI company. And as you'll be seeing, we're doing a lot with generative AI recently with Louie.ai. And before we go into, and actually make sure folks are in the right room, we will be talking about leveraging graph AI and GPUs to win the US Cyber Command AI Challenge. And so and this is actually updated since the talk was submitted. So this is sort of the Gen AI edition where we're actually been working on making this even more automated and kind of revisiting a lot of the methodology that we had done here. Before we go in too deep, I thought it'd be interesting to kind of just see who's in the, and learn who's in the room together with us today. And so maybe the first question is, red team, blue team, how many, anyone red team? So we got some red team, and I'm impressed you acknowledged yourself, so great. How about blue team? Any blue team? Like SOC, IR, threat? Okay. For anyone here, how about like Splunk or Elasticsearch? Do you use any of these like log search tools? So got maybe a third of the hands. How about SQL, or like especially Cloud SQL, like a Snowflake or Databricks or Postgres or anything like that. So, okay, that was like, I don't know if that was the same hands or the other half of the hands. But actually, yeah, how about a cloud SIEM? Is anyone actually moving to pushing towards like, Chronicle or Azure Sentinel or Databricks, anything like that? So we've got the innovator in the back, so awesome. And then on that, how about like Python? Anyone write Python? Okay, so we got like half the hands Python, Jupyter Notebooks, Pandas, all that stuff. Pretty much the same hands, like almost entirely the same hands. Out of those folks, anyone trained a machine learning model? Okay, did you hand write the neural architecture? Oh, we got one, two. Wow, okay, that's really exciting. So I wasn't even sure we'd get any, so that's really exciting. Okay, so as some quick backgrounds. Like I said, I was Leo, the founder of Graphistry, visual graph AI company, where you'll be seeing a lot about both Graphistry and Louie, where we're looking at just basically how do we work through the investigation process. About half of our users are on the kind of investigative side. We'll go all the way from security to fraud to misinformation, terrorism, human trafficking, like some pretty serious stuff. Actually, let me move that. And today we also have, I don't know, Alex, are you in the crowd here? So if any of this stuff is interesting and you want to track me down or our head of AI, Alex, he actually is Norwegian. And so for some of the folks in the audience, you might actually have a better conversation than with me. And what I'll be presenting today, even though generally we talking a lot of general technology and like kind of how we use data science in a lot of these security and investigative processes, a lot of the US Cyber Command competition was actually, it takes a team. And so I just wanted to highlight some of the folks who, most of them on the Graphistry team, but also Brendan was actually just a friend of the company, also was doing some great stuff. I know some folks like to take photos of talks we do, so we will be posting the slides later, so don't feel as compelled. You can also, find us online. Pretty much everything we're going to talk about today is open source, and so you can pip install Graphistry and get most of it. Math is math, it's universal. And then I do want to highlight two more sessions that are going to be interesting here. One is another friend of the company, Sindre's actually talk right in the next session. So he's going to be talking about how NC3, so Norwegian kind of defense group, government group, was actually using similar thinking for a recent, actually pretty major takedown. And then tomorrow, Alex is going to be doing a hands-on for a lot of the stuff we're going over today. So let's jump in. So about a year ago, we were invited to join this competition held by or sponsored by the US Cyber Command. So if you're not familiar with the US Cyber Command, they're basically half of the NSA building in the US, so it's kind of pretty important in terms of global cybersecurity. And they had an interesting challenge that was actually reflects of what we see a lot, especially if you're in a fusion center, but if any sort of operations center. And they're kind of asking two broad questions. So One is given a lot of this data, we'll get into it, they want to know a successful alert volume reduction solution will be capable of answering the following questions. Is an alert part of an ongoing incident? Is an alert part of an incident we've seen before? All these things that where you have this, all kind of the data, like kind of the daily, you pick up an alert or a ticket, like what is the context of that? So a lot of those kinds of stuff. And in their context, the reason they're even like having a bunch of teams kind of take a look at this is this actually maps pretty directly to a lot of their mission issues. How they deal with malware, user activity monitoring, kind of normal and abnormal operating conditions, exploit. No, just like it's just like a lot of checklists. Like this is basically correlation, which is the heart of a lot of blue team. Like how do you link together and correlate work? What was interesting to us, so we what's a little funny here was we were happy to be informed that we did get a first place finish. There's a few interesting things about how we did it. Most directly to these kinds of use cases, we'll be talking about this problem of alert volume reduction. It's like when you do have all these alerts, how do we correlate them so that you can just look at incidents rather than alerts? Or if you have an alert, how do you jump to that level? And kind of different views like incident boards, drill downs. But I think the big theme for the talk today is actually some of the methodology that was behind it. So we'll be talking about graph analysis and something called UMAP. Has anybody even heard of UMAP? We've got one person. So yes, this is like one of our favorite tools at Graphistry. So this is something you can do for free in your own team. So I think that'll be really cool. It gets to the heart a lot of classification and correlation work for event data. So we'll talk about that. And then underneath, really key to our methodologies are often keeping things visual, and then how do we make them kind of end-to-end GPU accelerated so we can keep things snappy and kind of work at these fun scales, but doing it in a way that's actually accessible. So with that, I want to kind of do before we go into how we approach the competition, I want to give a bit of a feel for the data. So we're working in the context of slightly anonymized Fusion Center data. So these are all alerts. This wasn't even events. This is already things that reach the alert level. We had about 16 million alerts from a period of 6 days from a few different locations we'll talk about in a second. Once they were kind of a little bit aggregated, and so if you unpacked each row a little bit, it was really about somewhere between 100 million and a billion alerts that we were trying to figure out what was going on. And it's actually pretty interesting data sets as far as they go. So it was contributed by CESNet, which is this kind of Czech threat intel sharing across a bunch of ISPs, telecoms, and universities. And so you can kind of see a lot of the targeted devices over here. And then, of course, cyber is kind of a global phenomena thing. And so here's everyone who is kind of triggering alerts, so it's around the world. Obviously, some areas are heavier. We see India, China, Russia. But basically, this is a population map of the globe, right? So I wanted to start with actually, to get a feel for the data we were working with, we're going to actually use Louie a little bit. And I'll compare this to how we did it within the actual challenge. So what I wrote here is, in the Databricks data, group the events by cluster ID, and for each group, and so some of our analysis, we're going to kind of bucket the alerts into clusters. Well, that'll be a big part of the talk coming ahead. And for each group, I'm asking, the first and last event time, the number of events, stuff like that. So I'm going to hit the run button here. Oops. Not sure. OK, here we go. Now we're running. We can tell we're running because this cool little strobe light. Has anyone used ChatGPT 4? I'm hoping. OK, everyone with a day job, basically. OK. So as this is running, we can kind of see in the background, like it's doing decisions like which database to talk to, picking which tables in the database to talk to. Like Louie's already kind of learned all that stuff. And then it's interpreting our question to map it. In this case, I had to generate the query. And then it decided that based on this question, not only did it need to generate the query, but actually needed to run the query and get us back the table of results. And so in this case, for example, I asked it again to kind of give us a leaderboard of all these different alert clusters. So we're seeing for each cluster ID, of course, if I wanted to inspect the SQL and stuff, we can. But for each cluster, we're seeing that, for example, cluster 26, we had 300 unique IPs, and just all the different breakdowns that I had, like, first, last events seen, like with all the time interval. What's kind of funny was last night when I was first running this query, somebody had actually set up this new cluster for me, and I was doing a quick data quality check. And we actually, I only had like 50 results in that data set, so somebody basically put in like, just the first page of data, and I was like, uh-oh. And so what I had done immediately after, and I just thought this was a good example of like how generative AI is like changing how we do this stuff a little bit, was I did something like, hey, Louie, do the same kind of analysis again, except now on the Splunk AVR 59K data set. So I want to switch from Databricks SQL to Splunk SPL. But I still want to answer that same question I was just doing. And so Louie here is interpreting what I just said. And I'm going to tie this back to why I think this is like kind of, to me, this is like mind-blowing in terms of the competition. So Louie's deciding, okay, we need to switch over to Splunk, and it's deciding what the task is. And then now it's going to look into Splunk and kind of generate that query. Just in the interest of time, I had just opened this ahead of time. And so what we got was kind of like if you know Splunk, it's not like the prettiest thing in the world, but it is like, Splunk, if I want to edit it, I could have edited it. But we got that clustering. And where I want to, so yeah, I'll connect that in a second. So, and then now we have like our interactive table, I can sort it, whatever. And so whenever we're going into a competition like this, or in reality just a customer scenario, or any sort of incident where you're kind of the surface area that we're sort of new to, like maybe it's like new environment or something, being able to quickly ask and answer questions like this and be able to kind of get a quick survey of things is pretty darn handy. So where I wanted to go with that was some of the next queries I had was I saw like all the events under, I think it was like cluster, I think 13 caught my eye last night. So 600 events, and then I thought it was interesting that we had like out of the 600 we only had like 60 unique source IPs. So I just wanted to dig into that. So I asked like, hey Louie, from that cluster, just get everything just in that cluster. And so now it's like we're actually getting to get a feel for what that data is. And so we're seeing in this check fusion data set, we're seeing like, okay, they've kind of already categorized the alerts for us. So we have a lot of like recon, some time range from that week. Each alert, again, is actually an aggregate. So like we're seeing each alert's actually summarizing like, potentially thousands of connections that were flagged. And we have like various other data. And so like this is kind of like from those whatever 100 million billion things, like a feel for the typical fusion challenge. This is not the easiest to read, obviously. It's a big table. You could dump it into Excel or something, but and so we did a few things here. So one of the things I asked Louie was draw a graph connecting the IPs to one another. So let's see if that loads. I'm actually gonna turn this off. Not sure why it's not loading. Okay. Well, it's more fun when it does load, but luckily last night I just pre-recorded a video, so let's jump ahead a little bit. So okay, just jump here. And hopefully later, like the live videos or even like the live sessions will work. So kind of what's shown here, like I had just asked it to draw a graph of all of the IP addresses in that data table, and so and we can kind of see here that I could have figured out the visualization tool or the Python tool to hey, given that data frame of alerts, treat the column of target. This is kind of funny. It's flipped. If I was going to do this more, I'd just ask Louie to flip the columns for me. But basically, I want to see the source IP for columns connected to all the target IPs. So this is all network data, right? And so here, what we see is basically a lot of these like little star, like this star field, where we have like one node, maybe like one source IP hitting multiple target IPs, and we're seeing this nice little star field. So that's like kind of getting the feel for it. So we know that there is a bit of, even at the network level, there is a bit of commonality in this data set. Let's jump ahead a little. Like there's more, if you think in terms of like IOCs and different kind of correlations in our data, there might be a bit more than just the alert name. And so, I'm sorry, the raw IP. So for example, often we know that when there's an attack happening, like maybe there's like an IP block of like that was kind of taken over at the same time, or that someone's targeting like kind of the same subnet of who the target is. Or like maybe there's like an alert signature or other things that we can kind of get commonalities. And so if we're going to have a graph to sort of correlate all these events, we can ask for this other stuff too. And so kind of as we're just trying to get a feel for the data set, we're kind of doing all these kinds of explorations just to understand. And so and there you saw I asked to do it in Louie. Here's kind of again, the recording from last night. And I'm just going to take all of these identifiers that from that data table that we pulled out from that text command, and then I'm just coloring by the category of data. Let me make this a bit bigger. And so what I'm kind of on the right here going through is like, we have IPs, subnets, categories, things like that, and the different colors correspond to the different kinds of data. And so you see in the middle, there's like those three, like one really common subnet, two really common subnets. And then also is all that recon scanning where the kind of the chief alert type. Here, I actually want to go a bit further. So let me pause really quick. That's a lot of like, if I was like in 1990s spy movie talking about how the NSA would do stuff back then, that kind of graph analysis is like that would have been like state of the art. Like where you have all these cool identifiers and you connect them together and you're like a crazy person like pointing at a pinboard, right? Of just like, here's like all this IP went to there, that kind of thing. A big theme of the talk today is more about the AI generation of that kind of technique, where let's say we've got a timestamp, or we've got the bytes, but someone's kind of trying to do some like malware polymorphism, and the byte count kind of goes up and down a little bit as they're kind of changing some identifiers. So all of a sudden now, instead of just these exact identifiers, we have these numerical things that are kind of varying a little bit. Like imagine like a botnet scan or something, like a port scan where the port range is just kind of incrementing. So now we don't want to just connect on the numbers, but like on the exact numbers, but the fact that there's like a sequence or like a time interval. So now I'm asking for something called UMAP, and we're going to talk about that, like what that actually means in a bit. But the important part is I'm saying, hey, look at the IP addresses, look at the timestamps, look at, and these are kind of these more continuous or numeric ranges, and I want to get correlations on those columns. And then the usual, a protocol IP address, like all those identifiers where you would kind of do the normal, traditional connect the dot stuff. So let's run that out. Just a fun Louie-ism, like whenever there's a data table in one of those investigations, like it has like an identifier, so when I'm asking it to do an action, I could just say which ID of the table. So in this case, again, we're going to talk about what UMAP actually does and what it means. But what it generated the code for me, again, I could manually write it in Python. Like that's actually at the competition what we had to do. But now with Louie, it's actually pulling out all of the things that kind of match my high-level command of what I wanted, like the different kinds of IP columns and protocol columns, and all the UMAP configuration. It's sort of filling in by default for me. And then, as before, it ran it, in this case, in a secure sandbox. And new features are like we're actually having it running in GPUs. So I'll talk about that. And this is kind of now a different kind of graph. So let's let this load a little bit. Now on screen, instead of it being like individual entities, like IP addresses and alerts, let me kind of go back a second. We're actually going to be, let's run that and then pause it. Each dot now is a event or an alert. And so every one of the rows in our query result is on screen. And they're connected if there's any, like the UMAP kind of figures out these correlations for me. So if any two alerts are somehow correlated across any of those dimensions I talked about, they're going to be connected here. And then the UMAP is going to figure out like, hey, let's put like things that are highly connected together, highly correlated on screen next to each other. And then I still want to understand the alerts and the IP addresses and stuff like that. So I could still do my normal like filtering, coloring, slicing, dicing on those dimensions. And so here, for example, I was curious about which alert category. So we saw there's just two categories of data, mostly the recon, a little bit of logins. Here I was curious about which subnets are, I forgot, it looks like target subnet. So we're seeing most of that red was about this all targeting the same subnet. But on these two clusters, we had a bit more of a few other subnets were getting targeted. And so we kind of, what's cool is like we're seeing that like the UMAP correctly separated out across these multiple dimensions in sort of a meaningful way. So imagine you show up at your shift and you've got like a big bag of alerts, or if you get a random Splunk or Databricks query result, like it just pops it out for you. So that was really cool. Okay, let's go back to why we're talking about this stuff. So for the challenge, we had 2 weeks. We actually thought it was just 1 week. And so having tools that are kind of ready to go and being able to actually win in just 1 week, despite not understanding what the scenario, it's important to have a lot of the tools set up. I was showing Louie. We didn't have Louie back then, so we had to do it all manually with Jupyter Python notebooks. And so we had to write manually code for everything. But what we did have was a lot of the environment, because we already prepackaged a lot of that environment, because this is the kind of setup we do. And so we just went to AWS, turned on the box. We had Jupyter, GPUs, database connectors, all the visualization, like all that was ready to go. We like to use these events to learn, and so we'll also be talking a little bit later. We found there were a few steps that were kind of slow when we were dealing at this step that we just had to, as part of our toolkit, we needed to add a couple more things. And so we'll talk a little bit about like graph neural networks, a new, it's actually we just announced last week, GFQL, a new graph query language that runs on GPUs. But basically, most of today, we're going to be talking about these techniques. And to me, it's also very impressive that for about $1 an hour, we're able to get like a single GPU. Like we didn't have to turn on like one of these big Snowflake or Databricks or like heaven forbid Splunk, massive deploys. This is just $1 an hour, and we're doing this stuff. And we actually had everybody banging on the same box. Louie, like I said, is new. Basically, it's letting us do in natural language almost everything we're talking about today. So this actually kind of scenario has been a big motivator for us to figure out how do we make a system where whenever we're using our favorite investigation tools like the UMAP I just talked about, the graph visualization, or if we're building out automations, how do we if we can teach the tools to the AI to learn those, then we can kind of focus more at the investigation level and work with the tools to take care of it. And if the tool could learn what our databases and our favorite kind of query sequences are, we can kind of work more at the level that we want to as investigators. So for the analysis, like the high level is we kind of like did a multi-phase flow. I can kind of walk through here. So we took our 100 million, billion, whatever events, but we realized like if you think about it from a kill chain perspective, that most attacks kind of go through similar kind of patterns. So for example, you can kind of classify the different phases differently. So for example, maybe at the beginning there's some scanning behavior, and then once they figured out what's running, they might do certain types of attacks. Like for example, maybe it's doing some scans, and then it figures out that, oh, we have log4j vulnerabilities. There's like Apache Tomcat or something running, and so then later we might see the log4j kind of exploit. And so from again, this like incident linking clustering, we're going to do a few phases of analysis. So first step is like for each kill chain phase, we're figuring out, could we link together events? So for example, for the recon activity, just like the network scans, what I was just showing you with that UMAP, that can kind of cluster stuff for us, right? And say, hey, if this all looks kind of similar scans, we can connect them. We're not just saying they're in the same group, but like here, actually, I just have, I'm not have a full triangle of things. I just have like a sequence, right? And so we can actually have like a cleverer and good linkage here. It is useful to say that they're all part of that same cluster, but when we're actually going to do things like timeline analysis and stuff like that, it's actually nice to have more of these like direct notions of like which are more related to the other. And we use different behaviors, so we'll have kind of these different cluster IDs here. Oops. And then once we have those, beyond like doing these like fuzzy linkages, then we could still do that classic, like if I was going to do a manual investigation or that 90s style thing, we could still take all of our IOCs and identifiers and link them together and realize, hey, the recon was on this 10 subnet, but so was this log4j, and it was actually the same particular two IPs especially. And so we can kind of link these behavioral clusters together, and that kind of lets us go across the phases of the kill chain, right? Recon to exploitation. We get a really big graph at this point, and so we also get kind of false positives, like data is dirty, all that stuff. And so we also want to then start cutting up the graph a little bit. But basically, at this point, we're saying, hey, once we have all these like kill chains stitched together, could we just draw bigger circles and just call those incidents? And because we have all these more direct linkages, that actually lets us kind of, hey, for the incident, incident group 200, let's drill in and actually get all the way to these granular levels. So that's kind of the big idea. And if you kind of scale it out, so for example, here I'm showing the MITRE ATT-CK, but if we're going to think about, for example, something like network scans, that might be part of like the reconnaissance phase or maybe the discovery phase. This case happens to work on network data. It's not obvious to folks, but actually a lot of the graph work is actually generally at the endpoint where you might have like files and processes and users like within a box. I'm just going to be using network examples today. But for example, if we have like a vertical scan, so we saw a lot of those, that would mean like maybe it's the same dest IP, but we're seeing that the port number is increasing, right? Like traditional graph analysis wouldn't work so well here, but because we have the UMAP, we can actually deal with the fact that it's just like that we want to link together same IP and kind of like that the correlated numeric range. And not only do we put them in the same group, we can sort of realize that there's this sequentiality. There's like this one, then this one, then this one. Like the UMAP gives us that kind of linkage. Likewise, let's say it's a horizontal scan, so that they're checking, they weren't trying to drill into an individual device, but maybe they're trying to see what's on our network. Now all of a sudden, they might be like probably like port 80 or something like that. But it'll be now doing the numeric range on the subnet level, right? They're just kind of looking at our block. And it's also kind of interesting from what's the converse, right? So before these kind of UMAP style approaches, like, and I'm sure this is what a lot of folks who are running their own systems would do, is like they might do more of a rule-based. And that's very kind of exploitable and attackable. So for example, if all of a sudden, like normally you kind of look at like, top attacking IP addresses because you're kind of looking at them, but for cheap, you can just get a botnet to do a distributed scan. And so you can no longer kind of use the IP address as like a quality IOC, right? Because they're just going to be getting for cheap. They could always just get fresh ones. Or like, for example, you can't just do like a small window of time function where we're just looking at the scan at a like short interval, because if they're doing like a low and slow, the scan might be over a longer period of time. And that by doing like Splunk or Databricks you might be able to do cost effectively, but Splunk or Elastic might be hard to do cost effectively. If you have to do a longer time range to do these correlations, that might make it hard. And so we don't really think about like manual rules that turn into like deterministically into alerts. What we're really talking about is think of these not as manual rules that are alerts, but thinking more about we're just trying to find correlations that later we may turn into alerts. So we're kind of separating the problem. Right now we're just correlating and trying to find very scalable ways to correlate. Yeah, I don't want to, just interest time, we do have some fun demos, but kind of for that UMAP, you're seeing different aspects of it getting highlighted. So they're all scans, same generally source subnet, but then kind of a bit more diversity in the target subnet. But we're seeing that UMAP was able to do that for us. I didn't define it, so I do want to be clear about it. So when we talk about UMAP, so that's universal manifold approximation and projection. The authors will technically describe it, which will make sense to maybe a total, and is a useful definition, but for maybe 3 people in the room. General nonlinear dimensionality reduction for locally smooth data. Translating a little bit, we're going to cluster across columns filled with steadily changing numbers and IDs. That's kind of like how to, I like to kind of describe it. So if you just have a really wide table with numbers, with identifiers or numerics, we're golden. And if you've used methods like this before, I'm guessing some more people here have used like k-means or PCA or maybe even TSNE. This is sort of like the last 5-year update to a lot of those. It just works better. I want to, underneath, share a little bit about, and this is more when we're in the RPE, the rapid prototyping competition, more of how we actually did it. Let me make this bigger. So here, instead of having Louie generate all this code for us, we had to actually manually do it. So obviously our productivity went down a little. So it's kind of funny to reflect on this like a year later. So we imported just graph stream pandas, both open source. We just loaded in this case, I'm just doing an extract. But now that we have that table of alerts, it's actually not a lot of code. Like we're like, hey, let's treat each alert as like one of our nodes in the graph. And then we're going to run UMAP on top of that to just kind of connect those edges, those alerts together with those correlations. And when I get back that kind of now, instead of just like a bunch of nodes, I now have connected nodes, so a graph. And then I could actually ask Graphstream to plot it, kind of what you saw in Louie before. that's it. Like, when we started Graphistry like 5, 10 years ago and we were doing these kinds of techniques, this would have been like many pages of Python and like these really monster notebooks. And so if you look at old data science tutorials, it was terrible. So it's been really cool that like there's just so much automation going on in these. And so I want to unpack a bit about what's going on. So even before we ran the UMAP, Graphistry is actually running something called feature engineering and vectorization. And so if you think of like all those columns, you might see like, let's say you have some Splunk or Databricks, whatever, like your SEAM result. Like, you have timestamps, you have IP addresses. What the feature engineering step does is kind of takes each one of those, like say an IP address, and turns it into just a straight up number. And often you'll see that we actually have multiple numbers for one concept. So we'll actually do a lot of different ones here. And if we actually had a graph and not just nodes, we would automatically generate features for the edges too, not just the nodes. And I'm going to get back to that in a bit. This can actually be a very slow process, but luckily, at least now it's automated. So that's already a big time save. Once we have all of these, again, the tool does it for us. I'm just kind of helping you see behind the hood if you ever wanted to play with it. Once we have like let's say we take those like 20 feature column, like 20 raw data columns, expand it into like 100 or 1,000 of these numeric columns. Again, the tool does that expansion for us. The reason we call something like UMAP a dimensionality reduction is we're basically saying like, hey, instead of having like 1,000 feature columns of these numerics, let's just map it to 2 columns, like we call them XY if we're getting a 2D picture, or let's just like compress it down to 3 columns like X, Y, and Z and have it in 3D. So that's why we call it not just clustering, but dimensionality reduction. We're just taking a really wide alert data and turning it into just like a scatter plot. So, and in particular here, you can see what I did is then I took our results and I said, hey, I want to get both the original data columns and also what the UMAP generated X and Y for each alert. And so you can kind of see that it figured out, imagine like each alert is like you're throwing alerts onto a dartboard. Like where does it land on the dartboard, which X and Y position, and it should be kind of near correlated alerts. Part of the way we do UMAP, we do kind of differently than a lot of folks who'll do it more from just like a purely theoretical perspective. We will then say, hey, if 2 alerts are highly correlated and they're really near each other, we're actually going to draw an edge saying that these things are correlated, and we're actually going to make that correlation a thing we could look at, play with, filter on, stuff like that. So we also have an edge table saying, hey, these two, like some alert 6671 to alert 638, they're like exactly the same, while another one might be like pretty similar. And so we'll actually get these weighted correlations out, and we'll automate doing that. So that's why we're getting graphs, not just scatter plots. And if you actually look into the UMAP methodology, that's kind of the assumption of what's going on underneath, is that the data does have this sort of connectivity going on. So this is why this stuff works. So something called a manifold. Okay. But again, you don't have, like, it's nice to know and dig in now and then because there are tricks you can play, but I just want to keep it at that level. Maybe one more thing I do want to mention, which is interesting. So people have used OpenAI. Has anybody used embeddings? So I've got like a couple hands. So anybody who's used OpenAI in large language models, you've actually underneath been using embeddings, because they'll take your natural language query, turn it into these really wide vectors I was showing you, all these numerics, and then that's how they work underneath. What's interesting about what I just showed you about the UMAP, we're actually doing that. So we'll run sentence transformers or whatever for you. So if it's a text column, we'll actually do the same thing. We'll actually, you can pass into OpenAI embeddings. So let's say you have like an incident report or a user report or like a threat intel description. That could be one of those columns, and that'll just be some of those numerics as just showing you. But then we still need to run UMAP after. So this is actually not instead of LLMs and Gen AI. This is part of doing that well. And this is kind of a framework to when we talked about this like 2 years ago, we'd be kind of crazy. But like nowadays, this is the methodology. Okay. Come to us after, or actually to Alex's talk to understand that a bit better. I'm going to show a quick demo. Remember in the UMAP I said we have to load in the data, we have to then turn it into like these like feature vectors, like expand it out into all these vectors, and then we run the UMAP, and then all that graph-tree visualization. When we did the RPE, all of it was already GPU accelerated, except for that conversion from alert data to vector data. We had to do that manually. After the competition, we're like, wow, like we were so bottlenecked on that step. So could we just automate it? And like, is there anything out there? So we found Dirty Cat, which will do automatic feature engineering, but it's CPU based. And so, and it has a, it's pretty cool. And I'd say it's more like inspiring. We actually forked it. But it's certain ergonomic issues, but also which we take care of in Graphistry. But importantly, it's slow. It's very slow. So what I'm going to show here is like we actually we're getting ready to do like the formal release, but we've already have the open source version out on a repo, what we call cuCat, so it's sort of the GPU reimplementation of Dirty Cat. We're hoping actually that we can get it landed in the main repo, so it could be more of a community thing. But I wanted to show here on the left and right. We're going to do that full UMAP flow where we take the alert data. On the left, we're going to do it mostly PyGraphistry GPU stuff, except for on the left, it's going to be with Dirty Cat for the feature engineering. And on the right, it's running cuCat, our GPU version. But it's that same one line of code, basically. But it's all about just accelerating the stuff. And so while they're both running, and again, we're doing the full pipeline, on the left, it's still running on the feature engineering. But on the right, it's already finished the feature engineering, moved on to UMAP, moved on to Graphistry, and it's done that full pipeline. And in the seconds, so it took maybe about 30, 40 seconds. We go all the way from the raw data to, see if yeah, so it took about 30 seconds. Let's just pause it right there to go from the raw data to this UMAP correlated stuff. While on the left, it was still just stuck on that CPU feature engineering step. So in our RPE, there's a few steps that we identified as sort of blocking us to really go quickly on these investigations. And so that was actually one of the biggest, the most burning one that came out of it. I do want to point out for folks thinking about UMAP, and kind of like a try yourself type of scenario, there's certain things that are kind of useful. So I already talked about the GPU acceleration. I don't want to go too deep into this one, but there's a variant of this, which is basically for anomaly detection, where let's say we have the UMAP embedding every day as people are logging into systems or people are using a website. Maybe it's a misinformation scenario. People are using a social network. Doesn't really matter what behavior event data we have. You kind of have like a shape of the data. Like imagine you have like a map, a contour map of what's the like a mountain range of that's just the shape of how things work in that region. Day over day, you kind of expect it to slowly change, but it's basically within a day, it kind of has the same shape. But if all of a sudden you have, for example, like a red team that's doing weird logins, or somebody's trying to do pen testers are trying to use strange port ranges or strange payloads or artificial or synthetic activity, you'll kind of stuff doesn't really land on the contour map. It just kind of, it's out in the ocean. It's just these weird clusters. And so we're actually able to use this UMAP for anomaly detection, not just for correlation. And so Alex will kind of go hands-on with that tomorrow. Going forward a little bit, just remember where we are in terms of the analysis. So we can now correlate things. We just spent like 15 minutes just talking about correlation, right? But now that we've done the kind of fuzzy correlation, we can now start turning stuff from kind of these kind of behavioral groups into incidents. This is a lot simpler because we now know, oh, is this the same user, the same IP address? We could just connect. Basically now we could just do more classic connecting of data. Just to give you a sense of what that looks like, so on the right here, there's some IP address. So now instead of showing alerts, we're just going to use the correlations as sort of edges to connect entities together. So we have some IP address here. In green, we have a lot of these kind of correlation IDs that we're basically doing all that mining for. And so, for example, this IP through 2 different correlation IDs is mapping to, looks like a bunch of domains over here, something like that. And so we could actually have, if we have lots of different UMAP models, like let's say some for network data, some from endpoint data, some based on just connectivity, whatever our correlations, we can now start connecting entities through the fact that we have these different correlation models or these UMAPs. And and having those concrete IP addresses and kind of more kind of stable things let us kind of connect them a bit better. Kind of fun is, I'm going to show kind of two views of the same thing. So here is the UMAP view of basically like we kind of made a leaderboard. Remember like that first Louie thing I said? It's like, hey, Louie, show me a bunch of these clusters in the Databricks data. And it gave me a bunch of those events in kind of clusters. This is sort of the expanded version. So I took the UMAP. Every node is an alert. Each edge is when any of those alerts are sort of correlated. And I think the coloring up there is, I'm actually not sure what stage refers to. But I think it's basically, I think it's, we took a look at like, hey, is this on the recon phase or is this on the exploitation phase? Like, where are we in the kind of the kill chain? So we kind of looked at for each cluster what the different kinds of alerts are in there, just to understand how far that incident group progressed. And so you're seeing that we kind of like in red, we have that's probably more recon. But what's interesting is that each group is sort of in clusters sort of uniformly clustered. And so even if there are multiple incidents within any alert group, we're actually again seeing that the labeling was pretty good. And when we kind of recolored based on maybe the alert type or the IP address, like the source or target address, like again, these like clusterings were kind of stable, which kind of tells us this grouping was sort of right. The reason I want to bring that up is like, okay, like let's say someone just gives you a big log dump of a bunch of like OS logs or alert logs, or you're walking into like, you're logging into a shift and you want to look at a bunch. It's kind of cool to be able to run and see the UMAP view and have it all together. But let's say I pick out one of those alerts, like, hey, there's like a bunch of like login related, let's say like, failed login related activity. Then the next thing we could do is jump into more of a zoomed in view where instead of just having zoomed out alerts, I actually want to have individual users, individual IPs, or individual file hashes, all of that put together and kind of have it a bit more zoomed in. So one incident, but all the backing correlations on it. So to be able to kind of, now that we have the linkages, we can actually build all those kinds of experiences. So that made the event a lot easier. Okay, jumping ahead. There's like the 1990s style connect the dots, traditional graph analytics. That was kind of a very kind of logical, kind of rule-based correlation. Then I showed you that kind of fuzzy UMAP-based correlation or any sort of embedding methodology, really. Pretty cool, a couple years ago is sort of kind of like a next level of this. Where we can actually do neural networks that do the same thing. And actually UMAP has like a neural model, come talk to us after. But basically graph neural networks are kind of a way to let us kind of actually automate a lot of the UMAP stuff and actually do a bit more learning within it. The level of big deal this is for example, like I'm sure most people have heard of protein folding, like fold at home, stuff like that. The Science's innovation or breakthrough of the year a couple years ago was graph neural networks for protein folding. The underlying architecture for graph neural networks is actually very close to, again, for OpenAI, their transformer model. These are kind of like variants of like very, very similar variants. I'll talk about that in a little second, but there's a lot of event data that in kind of physical data and event data that can be modeled on these ways. You're kind of getting a feel through this talk. Graph neural networks let us start doing much more targeted and advanced models for those things. As a kind of, so a few different domains, like in security, we often care about resource access. Like, is somebody logging in somewhere opening a certain file? How does different policies look? Maybe it's actually more at the kind of customer-facing level where we have a website and we have like customers and users accessing stuff on a website. Or like the fraud team, like we have transactions where people are kind of accessing wallets, or misinformation where people are talking to each other. All of the kind of examples I've done today, we basically said like, oh, we have interesting entities on screen, maybe that have some attributes, but we're just kind of correlating them. Graph neural networks lets us actually go a lot deeper into the attributes on each one, kind of like how UMAP let us do over the traditional, but we can also have attributes on the edges too. And so if we actually have some of that information, so for example, if we're trying to figure out like if we're trying to figure out account abuse or misinformation, kind of like these bad accounts and kind of when we have a bunch of interacting entities, it's actually useful to know, like, when, let's say on Twitter, like people are interacting, like, if there's a troll and, like, are they like ranting? Does somebody like someone or do they dislike them? It's not the fact that they're just connected, but is it a positive or negative connection? And so having this kind of data helps us beyond just kind of the clustering at the node level, if we can actually also have the relationships and include that as part of those methodologies. So GNNs let us start actually accessing this kind of stuff and do a much better kind of work. The reason I'm bringing that up, during the RPE, we didn't really have a good and accessible way to do GNNs. That's been changing. And so if you're interested in that stuff, again, go join Alex for his talk tomorrow. This has been, it's still, I think it needs to get better, but it's kind of the next wave. And when we have like a bit more time to work on a task, GNNs give us a way to get much better results. Another thing I want to point out from the RPE that was a challenge for us, like when I have that example of an incident graph of a bunch of like entities connected together, we want to do tasks now and then of like, hey, as an example, from an alert, can I pivot to which IPs, which users for that IP? Do those users have other alerts? And then what other IPs are associated with those? You can imagine all these kind of multi-hop things. It was really hard for us to do something like, it was easy to go to Databricks or something, get back 100 million alerts from some range we're looking at. But it's very kind of hard for us to kind of ask questions of like, these like scoping questions of like, if I want to connect the dots a little and hop out a bit, that was kind of really some pretty nasty data wrangling. So SQL, you can imagine doing a sequence of joins. That'd be both painful to write and also really slow. Pandas, Python pandas, we'd write that code a lot. You can do it, but it's kind of like Perl. It's like write once. Like you can write it, but you never want to be the one to pick it up from somebody else on your team, right? So being able to instead write it as a kind of like one of these like Cypher graph queries. One part of it is just being able to write something that like, from a user, hop forward to another kind of user, and then hop backwards to, or like kind of what I wrote with this thing. So this is something called Cypher. So it's a graph query language. One of the things that what's been frustrating is often when there are projects that need to do these kinds of queries, it's like, you've got your Splunk or your Elastic or your Databricks or your Sentinel or whatever. But to do this stuff, you then have to, again, go to some graph database vendor. You have to have extra infrastructure, and you have to pay them a whole bunch of money to do it for the pleasure. And now you have like 2 systems of records, and if your application's just bouncing between the two, and it's cool, but it's painful, right? So GFQL, we're able to basically just pip install as part of your normal pip install of Graphistry. You get our, all the stuff I was showing you. But one thing we released over the holiday was basically Cypher on data frames. So just as how when you're doing tabular stuff, you don't, like if you're doing the tabular manipulations of data for a dashboard or something, you don't have to round trip at the database to do every single little data wrangle. You can do that within your Python. We can now do that for the graph kind of, even if we got the data from a SQL database, if we do the UMAP or whatever to get the graph, we can then within the dashboard or analysis in memory, without having to add a graph database, do this kind of stuff. Pretty ridiculous is we did a trick to make it fast. We didn't actually expect it to be as fast as it ended up. So that's been kind of pleasant, where if you write something called vectorized data frame code, come talk to me about what that means after. It will, even the CPU version will actually do these bulk queries pretty well. Like remember the multi-hop expansion where every step out we get more IPs and more users. That actually, by writing it in a kind of vector data frame format, it's actually pretty fast. And so the engine will do that for you instead of you having to manually write that careful pandas. And we actually implemented it also in alternate mode, where if you pass in a GPU data frame, again, go to Alex's tutorial tomorrow about like all that's needed, and actually very little needed to do that. You'll get about roughly, on average, about a 10x speed up. And so we were able to do things like on 100 million, like we were able to take out like 100 million edges, think of 100 million events. And we were able to do basically sub-second or interactive time stuff on a really cheap, 5-year-old T4 GPU. This is like basically like $1 an hour on AWS. We didn't need a Spark cluster or anything to do this kind of stuff. So we covered a lot. I thought the RPE was like a really great example of like, if you really want to have a lot of this event data and really think about working more at the incident level and kind of a lot more intelligently, I thought it was a great kind of chance for our team to kind of get a feel for some, it's always good to have a challenge problem, but it was also a good chance for us to kind of spot some gaps in the ecosystem. And so it's kind of fun, a year later to say, hey, we've actually had a chance to those top 2 things we've actually already addressed. And it's actually, again, all open source. So I think a few kind of takeaways, I think, for folks here. So first is correlation is pretty core to basically any sort of security work or most forms. So hopefully you're getting a sense of the classical graph view where we're connecting identities, but also the modern, more AI view where we're having things like OpenAI embeddings or UMAP embeddings, things like that. That lets us then, instead of thinking about alerts and events, it actually gives us an automated and kind of principled way to work at the incident level and kind of go back and forth. And lots of applications, for example, detection engineering, this is a big deal. Another thing that's kind of, to me, been sort of interesting about the work is, yeah, we were able to, in half the time, basically, in the other teams, we were able to win just because we have a lot of the tooling ready. A lot of that Python burden is going away, where what you saw at the beginning with Louie, we still need to understand the methodology, and it's still you have to work with the data, and data is nasty in all sorts of ways, so it's not like the analyst is going away. But our ability to work with the tools and make the tools do things, the generative AI stuff, especially within Louie, it's a very different experience. And I think a lot of teams, you'll have the one person who does Python or these fancy notebooks, and then everybody else sort of, they struggle to adopt these methodologies within the team. We think that the generative AI stuff is going to be making this stuff a lot more accessible. So whether it's a junior staff member needing to learn a lot of the team's methodology, or maybe it's somebody who's senior and busy and they just kind of want to have a bit of help with the Python so they can focus on more of the actual task. And so hopefully you're getting a bit of feel for that. We are actually have started piloting with some different teams on using that. So if you use AWS or Azure or OpenAI, we're already able to do both cloud deployments, and we're also starting to work with government groups and banking groups on air-gapped systems as well. We generally prefer the kind of commercial cloud versions today, just because we get GPT-4 instead of GPT 3.5 quality models. But come talk to us after. We actually have stickers, so you could at least get that at the end of the talk. And the last thing I think is, again, we always like to, math is free. It's just about your brain. And then open source is awesome. We're long-term contributors. So pip install, almost everything I shared today is open source, including all the GPU implementations. GPUs are not free, unfortunately, one day. But hopefully that's a little bit of something for everyone here. And then, so again, I'm Leo. Come, reach out to me after. And we have Alex in the front here, and he'll be running a session tomorrow. And again, Sindre, I don't know if you're here, maybe. But next session today, in the very next track, we'll actually be talking about using some of these methodologies to actually do one of the biggest ransomware busts of I think, last year or the year before. So this, this stuff's pretty real. And again, thank you to the Graphistry RPE team, because as much as I've done a lot of this stuff, it takes a team. So with that, thank you. And, yeah.